The rocket is already lying, not in its numbers, not in its trajectory, in what it means that we built it at all, pointed it at a dead rock 384,000 kilometers away, and called it progress. But here's what I want you to sit with tonight. That rocket, the one we fired toward the moon with instruments and flags and the desperate confidence of a species that still didn't know what waited on the other side, it may be the most honest object humanity has ever produced. Not because of what it carried, because of what it admitted. It admitted we don't know where we are. And that question, the one baked into every mission we've ever launched into the dark, turns out to be far stranger than anyone in a mission control room was prepared to say out loud. Because the more precisely we've tried to locate ourselves in the universe, the more the universe has refused to give us a fixed address. Tonight, we're going to follow that refusal all the way to its edge. And when we get there, what you find isn't a wall or a void. It's a question so large that physics itself has to sit down. There's one part of this, near the end, that changes the way the word real works. Hold on for that. In the spring of 1969, a NASA engineer named John Aaron sat in a building in Houston, watching numbers on a screen that made no sense. The Apollo 12 mission had just launched, and 30 seconds after liftoff, lightning struck the Saturn V rocket twice. The instrument panel went almost entirely dark. Flight Director Jerry Griffin was about to abort. Aaron, who was 26 years old and known in the room for having an almost freakish memory for systems data, looked at the numbers and said something that no one else had said and that no one else in that room understood. He said, "Flight, try SCE to aux. Signal conditioning equipment to auxiliary power." It was a switch almost nobody knew existed. Astronaut Alan Bean found it. He flipped it. Every display on the ship came back online. The mission continued. Aaron knew that switch existed because 2 years earlier, during a routine simulation, a technician had accidentally triggered a power drop that produced almost identical gibberish on the screens. Everyone else in the room that day had walked away from the simulation confused. Aaron had walked away and quietly memorized the anomaly. He didn't know why. He just felt like something that strange deserved to be remembered. That instinct, to memorize the thing that doesn't fit, to refuse to walk away from the anomaly, is the engine behind every genuine discovery in the history of physics. And the anomaly that sits at the center of tonight's story is this. The universe is not pulling anything toward anything else. We think it's pulling. We've built entire civilizations on that assumption. But what if gravity is not a force at all? Stay with me, because this is where the rocket gets honest. In 1915, a 36-year-old patent clerk turned physicist named Albert Einstein published something called the General Theory of Relativity. He wasn't describing gravity as a force the way Isaac Newton had. He was saying something that sounds, at first, like a riddle. He was saying that massive objects don't pull each other. They bend the space between them. And other objects don't fall toward them. They travel in straight lines, through curved space. Here's how to see it. Take a flat bedsheet, stretch it tight across a frame. Now place a bowling ball in the middle. The sheet dips, sags. Now roll a marble across the sheet. The marble doesn't travel in a straight line. It curves toward the bowling ball. Not because the bowling ball is reaching out and grabbing it, but because the surface itself is no longer flat. That's gravity, according to Einstein. Not a pull, a shape. The Earth isn't falling toward the sun because the sun is yanking on it. The Earth is following the straightest possible line through a region of space that the sun has bent into a curve. From inside the system, it looks like attraction. From outside, it looks like geometry. And here's the part that makes the floor drop out. You aren't sitting in that chair right now because the Earth is pulling you down. You're sitting there because the Earth's mass has curved space-time, and the surface of the planet is pushing up at you through that curve. Gravity isn't pulling you down. The ground is pushing you up. You are being pushed upward at exactly the right rate to stay still. The sensation of weight you feel right now is not the universe holding you in place. It's the universe preventing you from following the path through space-time that you would naturally take. Which means the most natural thing you could do right now is fall. We've confirmed this, not just in equations, but in observations. GPS satellites have to correct for the fact that time runs slightly faster in orbit than on the surface of Earth, because gravity curves time as well as space. If the satellites didn't account for this, your navigation would drift by about 11 kilometers per day. That's not a theory. That's an engineering requirement. The curve is real. But here's where it stops being comfortable. If massive objects curve space-time, and if gravity is just the shape of that curve, then what is space-time actually made of? What is the fabric that's doing the bending? We don't know. Physicists have the most precise mathematical description of how space-time behaves that has ever existed. They can predict where a planet will be 1,000 years from now to within meters. They cannot tell you what space-time is. It's as if you could perfectly describe every rule of chess, every possible game, every outcome, and have no idea whether the board is wood or glass or even physical at all. And yet the strangest thing in this entire video is still ahead. Because the bending of space-time gets stranger the more you compress the mass doing the bending. Squeeze enough mass into a small enough space, and you don't just curve space-time, you break it. You create a point where the curve becomes infinite. A place where space-time doesn't just bend, it ends. A black hole. The term was coined in 1967 by physicist John Wheeler, who had a gift for naming things that stuck. But the mathematics behind it goes back to Karl Schwarzschild, who in 1916, while serving in the German army on the Russian front, derived the first exact solution to Einstein's field equations. He sent the solution to Einstein from a trench. He died 4 months later. The math survived. What Schwarzschild's equations described was a region around a sufficiently massive object where the escape velocity, the speed you'd need to travel to break free, exceeds the speed of light. And since nothing travels faster than light, nothing escapes. Not matter, not energy, not information, not time. Here's the image for that. Stand on the surface of Earth. Throw a ball straight up. It rises, slows, and falls back. Throw it faster. It rises higher before falling. Throw it at exactly 11.2 kilometers per second, and it never comes back. That's Earth's escape velocity. Now scale up the mass. Compress the sun into a sphere roughly 3 kilometers across. The escape velocity from its surface is now the speed of light. You have a black hole. The boundary where light can no longer escape is called the event horizon. And what happens to time at the event horizon is the part that should make you stop breathing for a second. Time slows down near massive objects. We've confirmed this with atomic clocks. A clock at sea level runs measurably slower than a clock on a mountain because the clock at sea level is deeper in the gravitational well. The difference is tiny, but it's real. Now extrapolate that to a black hole. As you fall toward the event horizon, from the perspective of someone watching you from far away, you slow down. Your clock runs slower. You approach the horizon, but never quite seem to cross it. You freeze. You redden. You fade. To the distant observer, you never fall in. You just stop. But from your own perspective, you cross the horizon. You fall through. You don't feel any single dramatic moment. You pass the point of no return, and for a brief while, perhaps, nothing around you seems different. except the future. Inside the event horizon, the direction toward the singularity isn't a direction in space anymore. It becomes a direction in time. The way you can't move backward in time outside a black hole, you can't move away from the center inside one. The singularity isn't a place you travel toward. It's a moment you're falling toward, a future you cannot avoid. And here's the part that's never taught in the way it should be. A black hole isn't dark because it's empty. It's dark because it's full of curved space-time so extreme that the universe stops making promises about what's on the other side. Now, black holes are extraordinary, but black holes aren't the strangest thing out here. After a star more massive than about 20 times our sun exhausts its fuel and collapses, the outer layers explode in a supernova. Sometimes what's left isn't a black hole. Sometimes the collapse stops short. What you get instead is a neutron star. A city-sized object containing more mass than the sun, compressed until its protons and electrons have merged into neutrons, packed so tightly that a single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. 1 billion tons in a teaspoon. Neutron stars spin. Some of them spin fast. We've found neutron stars rotating over 700 times per second. If you stood on the equator of one of these objects, you would be moving at roughly a quarter of the speed of light while standing still relative to the surface. Their magnetic fields are roughly 1 trillion times stronger than Earth's. But then there are the ones where even that stops making sense. Magnetars. A subset of neutron stars so magnetically extreme that their fields are roughly 1,000 times stronger than an ordinary neutron star. If a magnetar were the distance of the moon from Earth, its magnetic field would be strong enough to disrupt the iron in your blood. The field strength would override the chemical bonds holding the molecules in your body together, not burn you, not vaporize you, rewrite you at the molecular level before you had time to register anything at all. One magnetar, designated SGR 1806-20, released a burst of energy in December 2004 that reached Earth from 50,000 light-years away. It was a 0.2-second flash. In those 0.2 seconds, it released more energy than our sun emits in 250,000 years. It partially ionized Earth's upper atmosphere from across the galaxy. And that was a relatively quiet event for what these things can do. But even magnetars are local concerns, neighborhood phenomena. Because out at the edge of the observable universe, there are objects that make magnetars look like struck matches. Quasars, quasi-stellar objects, the brightest sustained phenomena in the known universe. The most luminous quasars outshine entire galaxies by a factor of 100, 1,000, sometimes more. A single quasar can output more energy than 1 trillion suns. They are powered by supermassive black holes at the centers of young galaxies, actively consuming surrounding matter. As material spirals inward toward the event horizon, it heats to billions of degrees and releases energy as radiation so intense it outshines everything else for billions of light years in every direction. The most distant quasar currently known sits roughly 13.1 billion light-years away. We're not seeing it as it is. We're seeing it as it was 13.1 billion years ago, when the universe was only about 670 million years old. We are literally looking into the past. Every telescope is a time machine. Every image of the deep sky is a fossil record. And here's the question that doesn't get asked enough. If we can see 13.1 billion light-years in that direction, and 13.1 billion light-years in the opposite direction, then the observable universe is roughly 93 billion light-years across, accounting for the expansion that's been happening the whole time light was traveling. We sit near the middle. We can only see as far as light has had time to reach us since the universe began. But beyond that boundary, the universe almost certainly continues. Physicists think the total universe may be vastly larger than the observable portion. Some models suggest it could be effectively infinite. The part we can see may be an almost arbitrarily small fraction of what exists. Every image from the Hubble Space Telescope, every galaxy we've cataloged, every quasar we've measured, all of it might be a grain of sand on a beach with no far shore. Now think about what that means for the rocket. In 1969, we fired a machine at the moon and called it the edge of human reach. In our best instruments, we can now see 13 billion years into the past. We can map the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, light that has been traveling for 13.8 billion years and still arrives at our detectors in a pattern that tells us what the universe looked like when it was 380,000 years old. We can read the universe's baby photograph, and in that photograph, there is a detail that stops everyone who sees it clearly. The universe, in its infancy, was almost perfectly uniform. Almost. Not quite. There were tiny fluctuations in temperature, tiny ripples of density. Those fluctuations, those almost nothings, are the seeds of everything. The galaxies, the stars, the quasars, the neutron stars, the magnetars, you. All of it grew from quantum fluctuations that occurred in the first fractions of a second after the Big Bang. The specific stars that formed, the specific planets that coalesced, the specific chemistry that produced life on at least one world, all of it traces back to quantum randomness at the universe's origin. Which means your existence is not a consequence of physics. It's a consequence of a specific role of physics. Had those initial fluctuations been infinitesimally different, the galaxies that formed would have been different. The star that became your sun might not have existed. The planet you're sitting on might not have formed, not in its current orbit, not with its current chemistry, not at all. And here's the honest part. The part the rocket was always pointing at without anyone saying it out loud. If time slows near massive objects, as we've confirmed it does, then a human falling into a black hole would age differently than a human watching from outside. The infalling person ages normally from their own perspective. The watcher outside sees the infaller freeze. Neither perspective is wrong. Both are correct simultaneously. Which means now, the moment you are experiencing right now, is not a universal constant. It's a local experience. There is no single now that applies to the whole universe. Different clocks tick at different rates depending on where they are in a gravitational field. Two people at different altitudes are experiencing different rates of time right now as you watch this. Some physicists, and this is where we're in theory rather than confirmed fact, think time doesn't flow at all. That what we call the passage of time is a feature of how we experience a universe in which all moments, past, present, future, exist simultaneously as fixed points in a four-dimensional structure. In this view, time doesn't flow like a river. The river is just there, all of it, already. And what you experience as now is more like a flashlight moving along a pre-existing path than a thing genuinely moving through time. This is not settled. This is not consensus. But it is taken seriously by serious people who have spent their lives on the math. If it's true, then the rocket we sent to the moon didn't travel through time to get there. It traveled along a pre-existing arc in space-time. The mission was already fixed. The outcome was already written into the geometry of the universe. Every choice, every accident, every human life. And yet that idea feels wrong in a way that's almost physical. It feels wrong because you are, right now, making a decision about whether to keep watching. That decision feels genuinely open, genuinely yours. Here's the reversal, the one I've been holding back. If the universe already contains all moments simultaneously, and if your experience of now is just a particular position on that fixed structure, then your sense of making a choice doesn't disappear. It becomes something stranger. Your deliberation, your weighing, your doubt, all of it is also already written into the structure. The universe didn't write a story in which you're a puppet. It wrote a story in which a creature arises that genuinely deliberates, genuinely wonders, and calls that wondering free will. The experience is real. The experience is fully embedded in the structure, and the structure doesn't care which one we call it. Carl Sagan said we are a way for the cosmos to know itself. After 13.8 billion years, after the Big Bang and the first light, and the formation of galaxies, and the ignition of stars, and the slow chemistry of planets, the universe produced something that looks back, that fires rockets not because it knows where it's going, but because something in its wiring will not stop asking. The rocket toward the moon is honest because it doesn't pretend to have arrived. It is always mid-flight. It is always a question aimed at something just out of reach. That's what we are. Not the answer at the end of the cosmos, the mid-flight question it keeps asking of itself. And somewhere out past the observable edge, past the quasars and the magnetars, and the geometry where time becomes a direction you fall in, the universe continues in ways our instruments cannot reach, and our mathematics can only gesture at. We know the laws that govern it are almost certainly the same. Same space-time, same quantum rules, same arrow of entropy pointing the same direction. But the contents, the specific arrangements, the specific rolls of the quantum dice that produced whatever is out there, we have no idea. If space is infinite, then every arrangement of matter that can exist does exist somewhere. Infinite space with random initial conditions produces, by mathematics alone, infinite copies of every possible configuration. Which means somewhere, in a region of the universe we'll never reach or see, every version of this moment is playing out. Every version of the choice you just made. Every version of the life you're living. Not as metaphor, as a direct implication of infinite space and finite physical rules. Physicists call this the level 1 multiverse. It requires no new physics. It requires only that the universe be large enough. And everything we've measured suggests it is. So the rocket we sent to the moon. In this view, every outcome of that mission exists somewhere. Every version where it failed. Every version where it succeeded differently. Every version where John Aaron didn't remember the SCE switch and the mission aborted. All of it real. All of it already written into the geometry. And here, 11 at night, in whatever room you're in, with whatever version of your life running in the background, you are the universe asking whether any of it was supposed to go differently. The rocket was honest because it didn't know if it would land. We still don't know where we're going. And maybe the most accurate thing anyone has ever said about the universe is the one nobody wanted to put on a mission patch. We are not navigating towards something. We are, all of us, still in the air. More Cosmos tomorrow. Be here. If this one kept you up, subscribe. It's free. It helps. And tell me what I got wrong, or what version of this I should have gone further with. I'll be in the comments.